PaddleOCR 3.0 Technical Report, PaddleCabal Team, Baidu Inc., PaddleOCR, Baidu.com. Abstract. This technical report introduces PaddleOCR 3.0, an Apache-licensed open-source toolkit for OCR and document parsing. To address the growing demand for document understanding in the era of large language models, PaddleOCR 3.0 presents three major solutions. 1. PPOCR v5 for multilingual text recognition, 2. PP Structure v3 for hierarchical document parsing, and the 3 PP Chat OCR v4 for key information extraction. Compared to mainstream vision language models VLMs, these models with fewer than 100 million parameters achieve competitive accuracy and efficiency, rivaling billion parameter VLMs. In addition to offering a high-quality OCR model library, PaddleOCR 3.0 provides efficient tools for training, inference, and deployment, supports heterogeneous hardware acceleration, and enables developers to easily build intelligent document applications. 1. Introduction Optical Character Recognition OCR is a foundational technology that enables the conversion of images containing text, scanned documents into structured, machine-readable text. Its significance has never been more pronounced than in the current era of artificial intelligence, where massive volumes of unstructured visual data are generated and consumed daily across scientific, industrial, and social domains. The recent surge in large language models, LLMs, and Retrieval-Augmented Generation RAG systems has further elevated the strategic importance of OCR. It is no longer sufficient for OCR systems to merely transcribe text. Accurately, they must now serve as critical enablers in the construction of high-quality datasets, facilitate knowledge extraction, and act as bridges between the visual and semantic layers of modern AI systems. The evolution of OCR technology reflects the broader trajectory of computer vision and natural language processing. Early OCR systems, based on handcrafted features and rule-based heuristics, performed adequately under controlled conditions but quickly reached their limits when confronted with the complexity and diversity of real-world scenarios. The advent of deep learning, particularly convolutional neural networks, CNNs, and their derivatives, ushered in a new era of data-driven OCR, enabling substantial improvements in recognition accuracy, robustness, and adaptability. However, as large-scale AI applications proliferate, new requirements have emerged. OCR engines need to handle a broader range of documents, from handwritten notes and multilingual content to rare or historical scripts, and complex layouts with tables, charts, and embedded images. Furthermore, in industrial and research settings alike, OCR is increasingly expected to support downstream tasks such as document understanding, key information extraction KIE, and semantic search, often as part of end-to-end intelligent workflows. In recent years, the rapid advancement of LLMs and RAG systems has fundamentally transformed the landscape of information retrieval and knowledge management. These systems rely heavily on the availability of high-quality, diverse, and accurately labeled textual corpora for both pre-training and inference. OCR, in this context, is not simply a data acquisition tool, but a linchpin technology that fuels the entire pipeline from digitizing vast archives of scientific literature to enabling real-time question answering over heterogeneous document collections. The accuracy and comprehensiveness of OCR outputs directly influence the performance and trustworthiness of LLM-based applications, especially in domains where information is predominantly shared in scanned or image-based formats, E.g., legal documents, historical records, scientific papers, and business forms. Moreover, RAG architectures, which combine retrieval mechanisms with generative modeling, are particularly sensitive to the quality of underlying document representations. Inadequate OCR can propagate errors, introduce noise, or omit critical content, thereby undermining the effectiveness of retrieval and the factual correctness of generated responses. Despite these pressing needs, existing OCR solutions still face significant challenges in practical deployment. Traditional pipelines typically struggle with low-quality scans, complex backgrounds, non-standard fonts, and multimodal documents that blend text with figures, tables, or handwritten annotations. The diversity of real-world languages, scripts, and writing styles further complicates the recognition process, requiring not only robust visual modeling but also powerful language understanding capabilities. In addition, industrial and research users increasingly demand lightweight, easily deployable solutions that can be adapted to different hardware constraints and integrated seamlessly with larger AI ecosystems. The open source community has played a pivotal role in democratizing access to advanced OCR technology, yet there remains a gap between academic research prototypes and production-ready systems capable of supporting the stringent requirements of dataset construction, RAG workflows, and large-scale document intelligence. PaddleOCR by Connex and Tudax. Advancements and innovations in open source OCR technology. PaddleOCR has emerged as a prominent open source project addressing these multifaceted challenges. Since its initial release in 2020, PaddleOCR has adhered to the principles of comprehensive coverage, end-to-end workflow, and lightweight efficiency, setting new standards for both usability and technical excellence in the OCR domain. Anchored by the PaddleOCR series, PaddleOCR has evolved through multiple iterations, each pushing the boundaries of text detection, recognition, and document analysis. Early versions such as PaddleOCR v17 focused on achieving an optimal balance between accuracy and speed, making OCR accessible for resource-constrained environments. Subsequent releases PaddleOCR v2, v3, and v4 incrementally improved recognition performance, extended language coverage, and introduced sophisticated models for handwriting and rare character recognition. A notable advancement has been the integration of document structural understanding via the PP Structure series, enabling PaddleOCR to move beyond text lines and paragraphs to address complex layout analysis, table structure recognition E.G, SLANET, and other advanced parsing tasks. These capabilities have made PaddleOCR a critical engine for automated document processing, intelligent archiving, information extraction, and increasingly for supporting the data pipelines of LLMs and RAG systems. The adoption and impact of PaddleOCR in both academic and industrial communities are evidenced by its widespread use and vibrant developer ecosystem. With more than 50,000 stars on GitHub as of June 2025, and its deployment as the core OCR engine in projects such as MinerU RAGflow and OCR PaddleOCR, has become an indispensable tool for digitization initiatives, knowledge management platforms, and AI-driven document analysis workflows. Notably, PaddleOCR has played a central role in the construction of high-quality document datasets for large model training, enabling researchers to assemble diverse, accurately annotated corpus spanning multiple languages, domains, and document types. Its modular architecture and rich API ecosystem facilitate seamless integration with RAG pipelines, where efficient and accurate OCR is essential for document ingestion, retrieval indexing, and context provision to generative models. As PaddleOCR's user base has expanded, so has the range of feedback and requirements from the community. Users have highlighted persistent needs in areas such as robust handwriting recognition, improved support for multi-language and rare script recognition, more powerful document parsing for complex layouts, and advanced key information extraction. These demands are further amplified by the growing scale and dynamism of LLM and RAG applications, where the ability to extract, structure, and semantically interpret information from diverse documents is a prerequisite for building reliable, responsive, and intelligent systems. Aware of these trends and our responsibility as a leading open source platform, we remain committed to continuously improving PaddleOCR to meet the evolving challenges of the field. PaddleOCR 3.0, a new milestone in enhancing text recognition and document parsing. In this context, we introduce PaddleOCR 3.0, a major release designed to systematically enhance text recognition accuracy and document parsing capabilities, with a particular focus on the complex scenarios encountered in modern AI applications. PaddleOCR 3.0 encompasses several core innovations. First, it presents the high-precision text recognition pipeline PaddleOCR v5, which leverages advanced model architectures and training strategies to deliver state-of-the-art accuracy across printed, handwritten, and multilingual documents, while maintaining efficiency suitable for both cloud and edge deployment. Moreover, PaddleOCR v5 achieves unified recognition of simplified Chinese, traditional Chinese Pinyin, English, and Japanese within a single model. Second, PaddleOCR 3.0 includes PP Structure v3, a document parsing solution that integrates layout analysis, table recognition, and structure extraction in an end-to-end framework, enabling accurate and scalable document understanding for forms, invoices, scientific literature, and more. Third, recognizing the need for deeper semantic integration, we introduce PaddleOCR v4, a system that combines lightweight OCR models with large language models to facilitate key information extraction, context-aware question answering, and lexible document comprehension capabilities that are essential for powering RAG pipelines and intelligent document agents. In addition, PaddleOCR 3.0 extends its coverage with dedicated solutions for specialized tasks such as sealed text recognition, formula recognition, and chart analysis, further expanding its utility for both research and industrial use cases. The contributions of PaddleOCR 3.0 are not limited to technical innovation. The release continues to prioritize openness, usability, and extensibility, with a robust API ecosystem, comprehensive model zoo, and active community support. In this version, several legacy design flaws have been revised to provide cleaner and extensible API and CLI, while maintaining a reasonable degree of backward compatibility. At the deployment level, PaddleOCR 3.0 has been restructured to deliver a more streamlined, out-of-the-box experience and improved integration capabilities with LLMs. By targeting key challenges in complex OCR scenarios and aligning with the fundamental needs of data construction for LLMs and RAG pipelines, PaddleOCR 3.0 aspires to serve as an efficient, intelligent, and open infrastructure for document AI. We hope that this advancement will accelerate the development of intelligent automation and knowledge-driven AI systems, foster new research and application frontiers at the intersection of vision and language, and promote document processing toward higher levels of intelligence and automation. 2. Core capabilities. PaddleOCR 3.0 comprises 3 core capabilities: PPOCR v5, PP Structure v3, and PP Chat OCR v4. This section elaborates on the problems addressed by these capabilities, details of the model solution, and their performance metrics. 2. PPOCR v5. PPOCR v5 is a high-precision and lightweight OCR system designed to perform effectively in a wide range of scenarios. It supports a diverse range of scripts within a single model, including simplified Chinese, traditional Chinese, Chinese Pinyin, English, and Japanese. To address the diverse hardware environments and varying requirements for inference speed, PPOCR v5 offers 2 distinct model variants, a server version and a mobile version. The server version is specifically optimized for systems equipped with hardware accelerators, such as GPUs, thereby enabling accelerated inference and higher throughput. In contrast, the mobile version is tailored for deployment in CPU-only environments, with optimizations targeting resource-constrained devices. Unless otherwise specified, all mentions of PPOCR v5 in this paper refer by default to the server version. Figure illustrates the framework of PPOCR v5, which comprises 4 key components: image preprocessing, text detection, text line orientation classification, and text recognition. The following will introduce these 4 components. 1. Image preprocessing module. The image preprocessing module is crucial for preparing the input images by enhancing their quality and adjusting distortions or orientation issues. This process lays a solid foundation for accurate text detection and recognition. PPOCR v5 includes an optional image preprocessing module to handle image rotation and geometric distortion. This module includes an image orientation classification model based on PPLCNet and a text-image unwarping model built on UVDocF. Users can choose to use these features based on their application scenarios. 2. Text detection model. The PPOCR v5 text detection model enhances its predecessor, PPOCR v4, through optimizations in 3 key aspects: network architecture, distillation strategy, and data augmentation. Firstly, PPOCR v5 adopts the more advanced PPHGNet v2 as its backbone network, replacing the previous PPHGNet. Moreover, PPOCR v5 enhances model robustness through knowledge distillation, utilizing a visual encoder from the advanced ISAO DOTRT.CRT as the teacher model to transfer knowledge by aligning feature representations with the PPHGNet v2 student. Finally, PPOCR v5 detection model enhances text detection performance by incorporating advanced data augmentation techniques, including hard case mining via ERNIE 4.5, VL424, BA47B comparison, and text line-based multilingual strategies, random synthesis, rotation, blurring, geometric transformations. Notably, PPOCR v5 detection model retains effective strategies from PPOCR v4, such as the PF head parallel fusion head architecture and the DSR dynamic scale-aware refinement training strategy. Overall, PaddleOCR v5 improves the model's ability to generalize across diverse datasets, leading to more accurate and reliable text detection in real-world scenarios. 3. Text line orientation classification model. In PaddleOCR v5, the text line orientation classification model is primarily responsible for determining and correcting the orientation of detected text lines. When the input text lines are misoriented, E.G, inverted, or rotated, this model can automatically identify and rectify their direction to ensure that they are in the standard readable orientation. This step guarantees that the subsequent text recognition model receives a correctly oriented text line, thereby improving the overall accuracy and robustness of the OCR system. 4. Text recognition model. The PaddleOCR v5 recognition model employs a dual branch architecture with PPHGNET2 as the backbone. One branch, GTC-NRTR, uses attention-based training to enhance sequence modeling in Python, while the other SVTR-HGNet focuses on efficient inference with CTC loss. During training, the GTC-NRTR branch guides the SVTR-HGNet branch, but only the lightweight SVTR-HGNet branch is used for prediction, ensuring both accuracy and speed. For data construction, PaddleOCR v5 combines traditional models with the ER&IE 4.5, VL 4.4, BA47B to automatically annotate and filter high-quality handwritten samples, including rare characters generated through synthesis. Additionally, large-scale labeled data is obtained from documents like PDFs and ebooks using automated parsing and edit distance filtering. These data construction strategies also provide a solid data foundation for the overall performance improvement of PaddleOCR v5. Accordingly, the core contributions of PaddleOCR v5 are as follows. 1. Unified multilingual modeling. PaddleOCR v5 achieves unified recognition of simplified Chinese, traditional Chinese, Chinese Pinyin, English, and Japanese within a single model. Through an innovative unified architecture design, the model maintains a compact size under 100 MB. This resolves efficiency bottlenecks caused by integrating multiple models in multilingual scenarios, significantly simplifying industrial deployment processes. An example illustrating PaddleOCR v5's multilingual recognition performance is shown in Figure 2, robust recognition of complex handwriting. To address the demands of key application domains such as examination grading in education, bill recognition in finance, and contract entry in the legal sector, PaddleOCR v5 has significantly enhanced its capability in handwritten text recognition. Experimental results demonstrate that, compared to previous models, PaddleOCR v5 reduces the recognition error rate by 26% on tasks involving non-standard handwriting forms, including both Chinese and English handwritten texts. Figure illustrates the performance of PaddleOCR v5 in handwritten text recognition. 3. Robust recognition of historical texts and uncommon characters. In complex and non-standard writing scenarios such as Chinese ancient texts and rare Chinese characters, PaddleOCR v5 significantly improves text recognition accuracy through optimization of network architecture and systematic construction of diverse, high-quality datasets, effectively meeting the high-precision text recognition requirements across various domains. The recognition performance in complex scenarios is shown in Figure. We evaluated the OCR capabilities across 17 different scenarios, including handwritten Chinese, handwritten English, printed Chinese, printed English, Chinese Pinyin, Japanese Chinese ancient texts, traditional Chinese, common, blurred, rotated, Greek characters, emojis, tables, artistic fonts, special symbols, and deformed scenes. These diverse scenarios allow us to comprehensively assess the performance and adaptability of the system. Based on the OmniDoc Bench OCR text evaluation standards, we conducted extensive testing on mainstream OCR methods and multimodal large models. Figure presents the evaluation results using one edit distance as the metric, and lists the average metrics across all scenarios as well as specific performance metric for key scenarios, including handwritten and printed Chinese and English, Chinese Pinyin, and Chinese ancient texts. The results indicate that the lightweight PaddleOCR v5 ranks first in terms of the average one edit distance across all scenarios, surpassing all multimodal large models such as JAS OCR 2.0 SAV, ROMOCR Swinpom, Phone to a Co.0 SAV B, Rosa 7.0 tone, with up for their fun. In Chinese scenarios, whether handwritten or printed, PaddleO5 CZ Prof. was slightly inferior to multimodal solutions in handwritten English recognition It is noteworthy that our model has only 0.07b parameters. In the Chinese pinyin and Chinese ancient text scenarios, PaddleOCR v5 has achieved significant advantages. These results demonstrate that lightweight models specifically designed for OCR tasks can match or even exceed the accuracy of large-scale multimodal models. Simultaneously, they offer substantially reduced computational and storage requirements, significantly enhancing inference efficiency and deployment flexibility, and thereby delivering critical advantages for industrial applications and mobile device deployment. 2.2 PP Structure v3. PP Structure v3 is a multi-model pipeline system developed for document image parsing tasks. It can accurately and efficiently convert document images or PDF files into structured JSON files and markdown files. As illustrated in the algorithm framework and figure, the system primarily consists of 5 modules: pre-processing, OCR, layout analysis, document item recognition, and post-processing. 1. Pre-processing. Similar to PaddleOCR v5, C-section PAs, this module comprises a document image orientation classification model based on PPLCNet and a text image unwarping model based on UVdoc. It is primarily designed to address issues related to low-quality document images, such as rotation and distortion. 2. OCR. This module employs PaddleOCR v5 C-section with pre-processing disabled to detect and recognize all textual content within document images. Compared to PaddleOCR v4, PaddleOCR v5 achieves significant performance improvements via optimizations in network architecture, training strategies such as knowledge distillation, and enhancements to the training dataset. Notably, it demonstrates substantial improvements in detection and recognition for challenging scenarios, including vertical text layouts, handwritten text, and rare Chinese characters. 3. Layout analysis. This module incorporates 2 models, a layout detection model and a region detection model. The layout detection model, PPDoc Layout Plus, is an optimized version of the PPDoc layout. It significantly enhances layout detection performance for complex documents, such as multi-column magazines and newspapers, reports with multiple tables, exams, handwritten documents, Japanese and vertically oriented layouts documents. The newly proposed layout region detection model addresses the problem of multiple articles appearing on a single layout page. For example, a single newspaper page often contains several distinct articles. Using only the layout region detection model makes it challenging to correctly associate elements with their respective articles, leading to errors in reading order recovery. By introducing the layout region detection model, elements can be accurately assigned to their corresponding articles. 4. Document items recognition. Based on predictions from the layout detection models, the content of each page element is recognized using appropriate methods, including the table recognition solution, PP Table Magic, the formula recognition model, PP FormulaNet Plus, the chart parsing model, PP Chart2 Table, and seal recognition with PaddleOCR v4 Seal. Table recognition. PP Table Magic is a comprehensive table recognition system composed of several specialized models. It includes a table orientation classification model and a frame type classification model, which determine the rotation and framing style of the table respectively, guiding the selection of the appropriate recognition method. The cell detection model, based on object detection algorithms, accurately locates individual table cells. Additionally, the structure recognition model outputs the table structure in HTML format. Formula recognition. This model is an enhanced version of PP FormulaNet capable of recognizing images containing formulas cropped from full document images and generating the corresponding LaTeX code. To address the recognition of complex multiline formulas, the token length was increased to 260 and the training dataset was expanded to include more complex formulas. Additionally, to handle formulas containing Chinese characters, a large volume of relevant data was mined for training. Chart parsing. PP Chart2 Table is a lightweight, end-to-end vision language model designed to accurately extract data from various types of chart images, such as histograms, line charts, and pie charts, and convert the extracted information into tables represented in Markdown format. It genuinely understands and retrieves chart data through an innovative, shuffled chart data retrieval task and meticulous token masking. Its performance is further boosted by a sophisticated data synthesis pipeline that generates diverse, high-quality training data using RAG with high-quality seeds and LLM persona design. A 2-stage LLM distillation process, leveraging large volumes of unlabeled out-of-distribution agent Kobu data, enhances the model's adaptability and generalization to real-world scenarios. Seal recognition. PaddleOCR v4 Seal is a system specifically tailored for the recognition of oval, round, and other types of seals. It incorporates a curved text detection model, which can accurately detect and rectify bent text, as well as a general-purpose text recognition model. 5. Post-processing module. Upon completion of the above steps, the positions and corresponding content of each element in the document are obtained. The post-processing module then reconstructs the relationships among elements, such as linking figures and tables with their captions, and recovering the correct reading order. PP Structure v3 improves upon the XY cut, significantly enhancing the reconstruction of reading order in complex layouts, including magazines, newspapers, and vertically typeset documents. To evaluate the performance of PP Structure v3, we conducted experiments using the OmniDoc Bench benchmark, with the results presented in table. As shown in the table, PP Structure v3 demonstrates exceptional performance in Chinese and English document parsing, establishing itself as the current SOTA. It not only significantly outperforms other pipeline-based tools, but also shows strong competitiveness when compared to the most popular expert VLMs and general VLMs. 2.3. PaddleOCR v4. PaddleOCR v4 is an advanced key information extraction solution for document images, leveraging LLMs, VLMs, and OCR technologies to enable robust key information extraction in challenging scenarios such as complex layouts, multi-page PDFs, rare characters, intricate table structures, and documents containing seals. As illustrated in figure box, the overall workflow of PaddleOCR v4 comprises the following components: the layout analysis module PP Structure, the vector retrieval module, the large language model ERNE 4.5, the document-oriented vision language model PPDoc-B2, and the result fusion module. 1. PP Structure. PP Structure serves as the document image parsing module. It is built upon multiple specialized models, including layout detection, text line detection, text recognition, and table structure recognition models. By leveraging these models, PP Structure is able to parse various elements from document images, thereby generating a structured, text-based representation of the document content. 2. Vector Retrieval Module. A feature vector database is constructed using the textual content parsed from document images. During key information extraction, RAG technology is initially employed to efficiently identify and extract critical information from lengthy and redundant texts. By leveraging RAG, the efficiency and accuracy of information retrieval are significantly enhanced. 3. Large Language Model. The framework supports any large language model, LLM for example. We currently use ERNE 4.5-300BA47B, the latest LLM released by Baidu, to extract information based on carefully designed prompts. These prompts are crafted to seamlessly integrate retrieved textual information with user queries, thereby enhancing both the efficiency and accuracy of the results. 4. PPDoc-B2. The PPDoc-B2 is a novel multimodal large language model with 3 billion parameters designed for end-to-end document image understanding developed by us. It is capable of directly extracting text-based answers from document images using prompts constructed from the given questions. 5. Result Fusion. Extraction results from both text-based and image-based approaches are fused to produce the final output. To evaluate the performance of PaddleOCR v4 and other methods, we designed an end-to-end evaluation pipeline using a custom multi-scenario benchmark dataset comprising 638 document images. These images span a wide range of scenarios, including financial reports, research papers, contracts, manuals, regulations, as well as humanities and science papers. Each document image is accompanied by several questions and corresponding answers, resulting in a total of 1,196 question-answer pairs. The results are presented in table. 3. Codebase Architecture Design 3.1. Overall Architecture. The overall architecture of the PaddleOCR 3.0 codebase is illustrated in Figure E to dot. At its foundation, PaddleOCR 3.0 is built upon the PaddlePaddle framework, which incorporates a neural network compiler for performance optimization, supplies a highly extensible intermediate representation IR, and ensures broad hardware compatibility. Building on this foundation, PaddleOCR 3.0 is structured around two core components: a model training toolkit and an inference library. The inference library offers flexible integration paths that naturally extend to deployment. The deployment capabilities will be introduced in section. The training toolkit provides a comprehensive suite of utilities that support the complete training pipeline for various models, including text detection models, text recognition models, etc. It also facilitates the conversion of trained models from dynamic graph format to static graph format, thereby enhancing their suitability for inference and deployment in production environments. Users can execute Python scripts with a single command to perform tasks such as model training, evaluation, and export. Additionally, various parameters can be configured to meet different requirements, such as specifying the path to a pre-trained model or using a custom dataset directory. Complementing this, the inference library is designed to be lightweight and highly efficient. It supports loading both officially released inference models and custom models trained by users. The library enables inference across 8 end-to-end model pipelines and can be readily integrated into real-world applications. We will elaborate the design of the inference library in the next subsection. The inference library serves as the foundation for downstream deployment capabilities, including high-performance inference across various frameworks, deploying the model pipeline as a service, deploying it to mobile devices, and running it via a Model Context Protocol MCP server. 3.2 Inference Library Design. In this subsection, we present the rationale behind the design and structural organization of the PaddleOCR 3.0 inference library. Let us start with the defects of the inference library. In PaddleOCR 2.x, all parameters of the PaddleOCR 2.x CLI exist in the same namespace. This is not extensible, as each new feature required manually adding more arguments to an increasingly bloated global parameter list, making it difficult to maintain and scale. In PaddleOCR 2.x, the parameters are only configurable through function arguments. Such an approach hinders reproducibility and portability, especially in scenarios where configurations need to be shared or version controlled. PaddleOCR 2.x lacks clear separation of concerns the boundary between the model development toolkit primarily designed for training and the inference library was not clearly defined. Instead, the inference library was built directly on top of the model development toolkit inference scripts, which introduced 2 entry points for the inference functionality, potentially causing confusion for users. Additionally, the inference library was constructed based on assumptions about what the entry points should be, which broke modularity and maintainability. To address these issues, we upgraded the inference library on top of the PaddleX 3.0 toolkit handwritten, which provides extensive inference optimization and deployment features. The backward compatibility was also considered, which minimizes migration effort for users transitioning from PaddleOCR 2.x. The new inference library consists of 3 layers, as illustrated in Figure Interface Layer. The library offers both a Python API and a CLI for user interaction. In PaddleOCR 3.0 CRTS, a reasonably a FIO-WAN. The library offers both a Python API and a CLI for user interaction. In PaddleOCR 3.0 2.x, the new inference library consists of 3 layers. As illustrated in Figure Interface Layer, the library offers both a Python API and a CLI for user interaction. In PaddleOCR 3.0, all OCR tasks are accessed through a consistent and unified Python API. To facilitate a smooth transition for existing users, the API preserves backward compatibility for key methods and parameters. The CLI has been completely redesigned compared to PaddleOCR 2.x, introducing subcommands that clearly distinguish between different tasks and thereby providing a cleaner, more intuitive user experience. Wrapper layer. This layer offers Pythonic wrappers for core PaddleX components, including models and pipelines. These wrappers deliver unified interfaces and flexible configuration management. In addition to maintaining the backward compatibility in the argument-based approach previously preferred in PaddleOCR 2.x, the PaddleX-style configuration file-based approach is also supported, which allows configurations to be stored and reused in a portable and reproducible manner. Foundation layer. At the foundation lies the PaddleX 3.0 toolkit, which forms the core of PaddleOCR 3.0. It offers powerful features for inference optimization and model deployment, which are fully integrated into PaddleOCR 3.0. Transferring the basis from PaddleOCR scripts to PaddleX ensures the separation of roles of the model training toolkit and the inference library, eliminating redundant entry points and clarifying functional boundaries. This decoupling allows each component to evolve independently, reduces user confusion, and lays the foundation for a more robust and maintainable system design. This layered architecture ensures that higher-level components depend only on lower-level abstractions, promoting loose coupling, modularity, and ease of maintenance. 4. Deployment and overview of the deployment capabilities of PaddleOCR 3.0 is depicted in figure. To support a wide range of application scenarios, PaddleOCR 3.0 offers flexible and comprehensive deployment options, including high-performance inference, serving, and on-device deployment. In real-world production environments, OCR-related systems are often subject to constraints beyond recognition accuracy, such as latency, throughput, and hardware compatibility. PaddleOCR addresses these requirements by providing configurable deployment tools that simplify integration across various platforms. In addition, to facilitate integration with LLM applications, PaddleOCR provides an MCP server, which allows users to leverage high-performance inference pipelines or pipeline servers. 4.1. High-Performance Inference PaddleOCR 3.0 provides the high-performance inference feature that enables users to optimize runtime performance without the need to manually tune low-level configurations. High-performance inference provides notable acceleration for some key models. For instance, on NVIDIA Tesla T4 devices, enabling high-performance inference reduces the single-model inference latency of PaddleOCR v5 Mobile RAG by 73.1% and that of PaddleOCR v5 Mobile DDET by 40.4%. Key features of PaddleOCR 3.0's high-performance inference capability include automatic selection of appropriate inference backends based on the runtime environment and model characteristics, including support for Paddle inference, OpenVINO FPaddleOCR ONNX runtime FPaddle inference, and TensorRT built-in optimization strategies such as multi-threading and FP16 inference to better utilize hardware resources. On-demand model conversion from Paddle static graphs to ONNX format to enable acceleration on compatible inference engines. Users can easily achieve inference acceleration by enabling the EnablePi switch, while all underlying optimization details are managed by PaddleOCR. For advanced needs, PaddleOCR also supports fine-grained tuning of high-performance inference configurations in pipelines by passing Python documentations or modifying configuration files. 4.2. Serving PaddleOCR 3.0 supports pipeline serving for building scalable and production-ready OCR-related services. Two solutions are provided. Basic Serving, a lightweight solution based on Fast API with minimal setup, suitable for rapid validation in scenarios with low concurrency requirements. For this solution, users can run any pipeline as a service with a single command via the CLI. For the client-side code, PaddleOCR 3.0 provides rich calling examples in 7 programming languages: Python, C++, Java, Go, Cyan, Node.js, and PHP. Users can refer to these examples to quickly integrate the service capabilities into their own applications. High-stability serving, a more robust option built on NVIDIA Triton Inference Server IDIA, which supports more advanced deployment configurations. This solution is suitable for scenarios with higher requirements for stability and performance. For example, the server can be configured to run multiple instances across multiple GPUs to fully utilize the available computing resources. Both solutions share similar interfaces. Users can start with a basic solution for rapid validation and then decide whether to adopt the more complex high-stability solution according to their needs, usually without significant migration costs. 4.3. On-device deployment. To support the deployment on resource-constrained devices, PaddleOCR 3.0 enables deployment of PaddleOCR models on mobile platforms. It provides supporting tools and documentation for model optimization and integration with the PaddleLite runtime, making it feasible to run OCR tasks efficiently on mobile devices. 4.4. MCP Server. PaddleOCR 3.0 provides a lightweight MCP server, enabling smooth integration of PaddleOCR's core capabilities into any MCP-compatible host. Both the OCR and PP Structure v3 pipelines are currently accessible as tools via the MCP server. Built on top of the PaddleOCR inference library, the MCP server supports various inference and deployment methods provided by PaddleOCR. At present, it can operate in one of 3 working modes. Local runs the PaddleOCR pipeline directly on the local machine using the installed Python library. This mode is suitable for offline usage in situations with strict data privacy requirements. High-performance inference can be activated to accelerate the inference process. AI Studio utilizes cloud services hosted by the Paddle AI Studio community. This mode is ideal for quickly trying out features, validating solutions, and for no-code development scenarios. Self-hosted connects to a user-hosted PaddleOCR service. This mode offers the advantages of pipeline serving and high flexibility, making it well-suited for scenarios requiring custom service configurations. Regardless of the selected working mode, setting up the PaddleOCR MCP server is straightforward for users. Example configuration files are included in the appendix for reference. Additionally, the PaddleOCR MCP server supports both STIO and streamable HTTP transport mechanisms, offering flexibility for a wide range of deployment scenarios. With its adaptable architecture and support for multiple deployment modes, the PaddleOCR MCP server can effectively address diverse real-world application needs, delivering robust and scalable solutions for both individual developers and enterprise users. 5. Conclusion. PaddleOCR has been dedicated to the field of OCR and document parsing for many years, aiming to provide more valuable technical solutions. PaddleOCR 3.0 is a milestone upgrade with technologies like PPOCR v5, PPStructure v3, and PPChatOCR v4 set to play a significant role in the era of large-scale models. Moving forward, we will continue to expand our models, including the upcoming release of multilingual text recognition models, multimodal OCR, and document parsing models. If you find PaddleOCR 3.0 useful or wish to use it in your projects, please kindly cite this technical report. Appendix A Acknowledgements. We gratefully acknowledge all individuals who supported this work through their invaluable contributions to data construction, deployment, testing, project maintenance, product development, online demo creation, and operations. Their dedication and efforts have played a crucial role in the successful advancement and ongoing improvement of this project. We would also like to acknowledge the invaluable contributions of open-source developers on GitHub, including but not limited to Timinator, Lacking, Opala, Co63, OC, JK4E, and many others whose work has inspired and supported our project. Finally, we express our sincere gratitude to all project contributors for their long-term support and valuable input. Their efforts have greatly advanced the development and improvement of this project. Figure shows the avatars of these contributors as collected from the PaddleOCR GitHub repository. B. Usage of command and API details. To use PaddleOCR 3.0, you can simply install the PaddleOCR package from PyPI. PaddleOCR 3.0 provides command line interface CLI and Python API for users to use conveniently. B1. Run inference by CLI. We provide convenient CLI methods for users to quickly experience the capabilities of PPOCR v5, PPStructure v3, and PPChatOCR v4 as follows. B2. Run inference by Python API. We also provide a clean interface to facilitate users in using and integrating it into their own projects. 1. PPOCR v5, example C. More details on MCP host configuration. Here are several example configurations for the MCP host in Claude for desktop, illustrating how to connect to a PaddleOCR MCP server. Each configurable parameter may be specified either via environment variables, as shown in the N field, or via command line arguments, as shown in the args field. 1. Using the local Python library. 2. Using a Paddle AI Studio service. 3. Using a self-hosted service.